Hello, my name's Adam. I'll be presenting the proposal for my study of the comparison of independent component analysis algorithms for use on EEG data, and this will be across 3 domains of performance. Independent component analysis for use with EEG is of particular interest to the field of psychology and behavioral neuroscience because it, one, allows us to remove artifact that would usually obscure us reading the data, and 2, potentially give us the opportunity to begin to observe independent signal generators in the brain. I'll be going over 2 broad subjects in this presentation. The first will be the previous research. I'll also be going over the history, the methods used in that research, and the strengths and weaknesses therein. I'll also cover the current study that's being proposed, its purpose, hypothesis, design, procedure, and its limitations. Starting off, I'll talk about the previous research. I'll be covering what was existing before ICA, the inception of ICA, ICA for use in source separation, ICA for use in EEG source separation, and comparative studies. I'll start with what was extant before ICA. There were a few things that preceded ICA that eventually led to the inception of ICA itself. PCA was created by Carl Pearson in 1901, and PCA was used and is used for exploratory data analysis and the reduction of dimensions of data sets. It was created by Carl Pearson, who's better known for having contributed to statistical methods like correlation coefficient, chi-squared test, and hypothesis testing. The first implementation of an artificial neural network happened at MIT in 1954. Artificial neural networks came about as an attempt to simulate intelligent behavior through modeling organic brain networks. This was done using 2 core concepts. One was threshold logic, and threshold logic takes a continuous flow of data from at least one input, and it outputs one discrete stream. The neural networks were also modeled after Hebbian theory of connectivity and learning. In the image to the right, you can see one of the earliest neural networks called a perceptron. That's a picture from 1954. Now I'll talk about ICA's inception. ICA was first introduced in 1984 by Bernard Ons and Jenny Arrow in a paper titled Neural Network with Modifiable Synapses, Decoding of Composite Sensory Messages under Unsupervised and Permanent Learning. It was introduced in the context of the field of theoretical biology as a possible approach to finding the primitive entities that made up a mixed signal. To the right, you can see a few snippets of the title and abstract. The original paper was in French. Next, I'll cover source separation using ICA. The authors who proposed ICA originally in 1984 went on to apply image source separation the following year. This image to the right isn't from that study, but it's an example of how ICA can be used to separate 2 mixed images. The top row is the original, the middle are examples of it being mixed, and the third row is an example of what is the output. So not until 1994, when Pierre Common's paper titled Independent Component Analysis, a New Concept, did the idea of using ICA begin to catch on in the academic world. ICA saw a large increase in attention from academics who sought to apply it in a variety of fields afterward. Next, I'll talk about ICA specifically for EEG source separation. ICA has been applied to EEG to separate source components since at least 1996. Many variants of ICA had been developed, many of which have their own subvariants. Since there's been such a wealth of algorithms developed, studies comparing the various algorithms began to pop up in the context of a variety of brain-related fields. These fields include behavioral neuroscience, brain-computer interface, and cybernetics. Next, I'll talk about the comparative studies. In studies that compare ICA algorithms, measures of performance that were relevant to the specific field or context from which the authors were writing from were used. Measures of performance assessed independence of components as well as the efficiency of the algorithms. Next, I'll talk about the strengths, weaknesses, and the core issues that are present in ICA currently. First, I'll talk about the strengths of the comparative research. There are many divergent brain-related fields that are interested in using ICA, all who value different performance measures. Because of that, there are a wealth of descriptive performance measures to observe. Because ICA is inherently computational, the measures of performance do not require effort put into operationalization, since they are looking at clear data that does not need to be interpreted or passed through human perception before analysis. Now I'll talk about the weaknesses. The main weakness in the research regarding this topic is that previous studies that compare ICA algorithms have not been comprehensive in either their inclusion of algorithms or measurements of performance, and that's part of the main thing that will be addressed in this study. And now I'll talk about the core issues that still underlie ICA today. Since ICA is being applied to real EEG data, there is no ground truth with which we can compare the output with. This makes it impossible to know how close we really are to reality. The problem of source separation using ICA or any blind source separation algorithm still stands as an unsolved problem. Thus, there is no perfect algorithm to use in every case and every application. Next, I'm going to talk about the study that I'm proposing. To do so, I'll talk about the purpose of the study, the hypotheses, the design, the procedure, its limitations, and also some further study after this study. For the purpose of this study, the primary goal is to bring the current knowledge base of ICA up to date with the current algorithms that exist. In doing so, a number of other goals will be attempted. In running this study, standardizing the methods used for comparing algorithms will be attempted. Another goal is to make ICA more accessible. Oftentimes, the clinicians and researchers who are applying ICA are coming from backgrounds in psychology, a field that is not inherently technology-oriented. For many, ICA can be quite intimidating to try and understand if the only way to go about it is to dive into the technical literature. Lastly, unifying the disparate fields of psychology, neuroscience, and biotechnology in the discussion of ICA application is a desired outcome. Next, I'll talk about the hypothesis. The primary hypothesis is that Picard, the most modern of the ICA algorithms that are being compared, will be the best performing. The logic behind this is that because it is most modern, the creator has had the chance to consider all previously created algorithms and work to make something that is better. An alternative hypothesis is that there will be no single best performing algorithm, but rather a cluster of algorithms that lead the pack, but each have their own strengths and weaknesses. Next, I'll talk about the study design. The study design is an experimental one, and it will use 3 different types of test data and look at 3 domains of performance variables. First, I'll talk about the experimental design. The study will be a repeated measures design. Selection of real data will be systematically randomized, as well as the simulation and creation of the other data test sets. The data sets will be treated with the 20 different algorithms, and the performance outcomes will be compared. Next, I'll talk about the types of test data. 117 data sets will be treated with each algorithm. 39 EEG recordings will be randomly selected from Stanford's OpenNeuro open source BIDS database. 39 different EEG recordings will be simulated using the neuroelectromagnetic forward head modeling toolbox from EEG Lab. 39 composite images will be created with randomly weighted source components. Next, I'll introduce the variables that will be measured. The 3 domains of performance will be efficacy, efficiency, and complexity. First, I'll talk about efficacy. Efficacy will be assessed using a variety of measures. The 2 broad categories are independence and dipolarity. For independence, entropy, negentropy, kurtosis, root mean square error, and correlation coefficient will be measured. To assess dipolarity, mutual information reduction will be measured. To assess efficiency of the algorithms, both time and memory usage will be measures. For time, both total runtime and rate of convergence of the algorithms will be measured and reported. Complexity is the only novel performance measure that will be introduced in this study. In order to assess complexity, Big O notation will be used. Big O notation is a technique that assesses projected performance of programs and algorithms. This is done by breaking them down into the data structures and functions used. The understanding developed about each of these components' performance is summed to deduce the worst-case scenario in regard to complexity. By seeking these measurements, we are able to assess runtime and memory usage in a meta way that removes the need to consider individual machine performance. Temporal complexity is analogous to runtime, while spatial complexity is analogous to memory usage. Next, I'll talk about the procedure. Each of the 117 datasets will be treated with 20 different algorithms. The results from each of the different types of data sets will be averaged, visualized, and compared between algorithms. The process of running all of the data will be automated as much as possible to remove any human error and to cut down on the duration of the study. Next, I'll talk about the limitations. One limitation of the study is that it will be done using MATLAB and not with other languages like Python, R, or Julia. The result of this is that there will be a performance difference between this study and the performance if the algorithms were to be implemented using another language. This also means that there will be a syntactical difference between what is implemented in this study and what might be implemented by someone else. Another limitation is the hardware that will be used to run the study. The workstation that will be used is very high-powered and would likely not be comparable to most real-world applications. This will result also in differences in performance when compared to real-world implementation. I'll now talk about combating these limitations as well as the justifications for accepting these limitations. In order to combat the language limitation of this study, great effort will be spent in staying true to the implementation from the original algorithms study. Along with this, best coding practices will be observed and readability and translatability will be strived for. The hardware limitation is one that was accepted with the assumption that, while external validity might be decreased, statistical validity would be increased since the workstation will be able to run the algorithms with high consistency. The measurement of complexity also combats the limitation since it disregards the need to run the algorithm altogether. Next, I'll talk about further study. Using the new standardized framework, the methods of this study can be replicated for use in assessing and comparing subvariants of ICA algorithms, as well as non-ICA blind source separation algorithms. The knowledge gained from this study will also set a solid foundation for developing novel ICA algorithms that will outperform the current algorithms available. The study will also lay the groundwork for being able to study the specific components of each of the very high-performing algorithms in order to understand on a deeper level how we might pursue the real solution of the source separation problem. That concludes my presentation of the study. Thank you.